All right, so it's Hessel, and we're back with another solutions video. This time from Brief Review in Physics, which is a physics workbook that has some extra problems, and that's where I got this from. So it's pages 31 to 34, number 6, 8 to 19, 22 to 26, focusing on kinematics with a particular focus on motion graphs. And so just remember, even before we do number 6, let's talk about motion graph strategy in general. Don't forget that when you see a motion graph, you'll know it's a motion graph because you'll see the graph plotting something against time. And that's kind of the point. The first thing you want to identify is what is that something? What type of graph is it? So we have 3 different types of graphs, and all of these guys are against time. D versus T graph, V versus T graph, and A versus T graph. Of course, D is distance or displacement, V is speed or velocity, and A is acceleration. But I'm going to drop the versus T because they're all against time. We can measure against other things, but time is the ultimate independent variable. We frequently measure against that. And by frequently, I mean usually. We usually measure against that. And so if we have, for instance, a D versus T graph and we need to find velocity, we take the slope. So D versus T graph, we need to find velocity, take the slope. And then similarly, if we have a V versus T graph and we need to find acceleration, again, we take the slope. But then going the other way, if you have an acceleration graph and you need the velocity, so instead of having a velocity graph and needing acceleration, the other way, if I have an acceleration graph and I need the velocity, then I break the graph into shapes, into triangles and rectangles. I take the area under the curve. That type of question doesn't come up that often. But what does come up more often is if I have a velocity graph and I need to find distance or displacement, I take the area. And so that's kind of like the common strategies. But all right, let's start with number 6 and we'll go from there. We're looking at number 6. Like I said, the very first thing we do is identify the graph. This is a distance versus time graph. Okay, cool. And then we see and when we're doing like plug in and solve problems, like number 7, 7 is not one of the ones that we were selected, but if you look at 7, it's like, starts from rest, V initial is 50, T is 5. We write down our given information. You don't really do that with a graph question because the given information is really kind of given in a graph format. So we just kind of jump straight to the question. Now for number 6, it wants to know what is the speed. So what is the speed specifically from 2 to 4 seconds? And so my first thought is if I have a D versus T graph and I'm looking for speed, I take the slope. That's what I said over here. If I have D versus T and I need to find the speed, I take the slope. Look at the slope from 2 to 4 seconds. I work out that slope. I wind up with 10 as my answer. Of course, I know that I'm talking about speed, so my units will be meters per second, and that is choice 4. Somebody could argue, is like, oh, do you have to do the slope? Can't you just do like D over T? Doesn't V equal D over T? And just do D over T. Yeah, of course. It goes 20 meters in 2 seconds. So we do 20 meters in 2 seconds, you get 10 meters per second. So either approach works. Either way. Okay, so some of these deal with motion graphs, but not all of them. Now, for instance, number 8, there's no motion graph to look at. It's not a motion graph question. All right, this is all kinematics in general. So it's just a general kinematics question. It says, what happens if you have 0 acceleration? All right, well, first of all, we have to understand what acceleration is. How do you know if you have 0 acceleration if you don't know what acceleration is? Well, we should know that acceleration is a change in velocity over time, but we always take things over time. And just to be clear, that's all well and good if somebody's like, oh yeah, acceleration's change in velocity. And I was like, cool, what's velocity? And they were like, I don't know. So then, change in something without it, don't know what it is. So velocity, we know, is speed with a direction. And that direction could be as simple as positive or negative, like forwards or backwards, which for one-dimensional kinematics is pretty much what we stick to. But anyway, so the problem said we had 0 acceleration. So if acceleration is a change in velocity and you don't have any acceleration, that means there is no change in velocity. And so if we have 0 acceleration, 0 change in velocity, which means that our velocity is constant. Notice I said that the velocity is constant. I didn't say that it is constant. And that's why when you guys say it, I try to discourage you from saying it. You have to be specific, because you could say the velocity is constant, which means the acceleration must be zero. But then if you say it is constant, you might be talking about the acceleration, in which case maybe the velocity is changing. So we have to be specific when we say it. Anyway, zero acceleration means a zero change in velocity, and our velocity is constant. All right, I didn't even look at the answer choices yet. So, answer choices. Object must be at rest. So if your must be at rest, that means your velocity has to be zero. If you have no acceleration, that means your velocity is not changing. It doesn't mean that you have to be at rest, it just means that your velocity can't be changing. So no, it's not choice 1. All right. Choice 2 says the object must be slowing down. No, that can't be right, because zero acceleration means there's a zero change in velocity. Slowing down is a change in velocity. It's a change in speed. So yeah, that is accelerating. That is not zero acceleration. So no, it's not choice 2. Oh, so now they're getting cute with number 3. Instead of must, they're using the word may. So it's possible. All right, whatever. What's possible? The object may be speeding up. No, it can't be speeding up. We have zero acceleration, so there's no change in velocity, no change in speed. So no, it can't be speeding up. So no, it's not choice 4. Choice 3, that leaves us with choice 4. And that is actually our answer. It may be in motion, which sounds kind of like general and vague, but it does work. If you have no change in velocity, then two things could be true. So if your velocity is constant, two things could be possible. Your velocity could be zero, you could be at rest, which if you're at rest, your velocity is constant at zero, or you could be moving, but with a constant velocity. So choice 4 is right. You may be in motion. You may be at rest, or you may be in motion. But yeah, so it is choice 4. Number 9. Number 9 is one of the problems I mentioned before about how we write down our given information, and based on the givens and the unknown, we choose the equation. So 9 is a classic. Let's take a look. Through the problem, we have an accelerating particle. That's fine. You could draw a picture if you want. I don't know if that's necessary. I'll draw one anyway, just to for clarity. All right, so we have an initial condition and a final condition. We got our particle. V initial is 8 meters per second. V final is 28 meters per second. And it doesn't specifically say that those are speeds, but I can tell that they're speeds based on the units. I know that meters per second measures speed and velocity, and so those would be speed and velocity, initial and final. I can tell that we are speeding up. We're going from 8 meters per second, so in the beginning, to going really fast at 28 meters per second later. So it is accelerating. It tells us the acceleration is 2 meters per second squared. I know that because it says acceleration of 2 meters per second squared. Also the units, meters per second squared, go with acceleration. All right, it doesn't tell us how far. That's fine. We don't need to know it. You'll see why in a minute. So what are they asking for? They're asking for the time. So I have V initial, V final, and acceleration, and I need time. Formula on page 6 of the reference tables is Vf equals Vi plus At. I have, of those 4 variables, I know 3 of them. T is unknown. Let's solve. Put my numbers in and substitute with units. I'm trying to get T by itself, and so I'm going to subtract 8 from both sides. And I wind up with a final answer of 10. Since it's time, that would be 10 seconds. And it's not a multiple choice problem, so we just kind of box the answer. You don't have to use that equation. There's actually another equation you can use, A equals delta V over T, also on page 6 of the reference tables. Remember that delta means final minus initial. Either way it works, you still should wind up with 10 seconds. So that is number 9, right there. Okay, we're at the bottom of this page right here. Alright, new page. Okay, so for number 10 we have a car, an object going east, and it's slowing down, and it wants to know what's the direction of the acceleration. So you have to remember, with acceleration direction, it depends on if the object is speeding up or slowing down. So if speed is increasing, if you are speeding up, then the direction of the velocity and the acceleration, they're in the same direction. And if your speed is decreasing, then your velocity and your acceleration are in the opposite direction. So that's the rule of thumb. So let's get back. It said that our object was traveling east, but its speed was decreasing. It was slowing down. So that means the acceleration is against the direction of motion, not with the direction of motion. So slowing down, going east, the acceleration must therefore be west. All right, 11. Actually, 11 and 12 are based off the same graph. Graph is a v versus t graph. Just as a rule of thumb, we know that the slope of a v versus t graph, area under the curve, is the distance or displacement. Right. Knowing those things, let's take a look at number 11, acceleration from 10 to 15 seconds. Well, we know the acceleration is the slope, and we're looking at 10 to 15 seconds. So there are no numbers on this graph, but I'm looking for the most slope, or the steepest slope. Clarify, we're not looking for the amount of the acceleration from 10 to 15 seconds. We're looking to see which one had the greatest acceleration from 10 to 15 seconds. Well, I can see that car A has no slope, so car A isn't accelerating at all. But I can see that car D, while car D didn't do anything for the first 10 seconds, D then started flying from 10 to 15 seconds and beyond, eventually becoming the fastest car of the bunch. But D has the steepest slope from 10 to 15 seconds. And so the answer is car D. And so reading this graph, I can see that even though A was the fastest car when time started, and A was like really flying, D just kind of like sat there for 10 seconds, just like la 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 la, and then D was like, let's go! And then D like started speeding up, and even though A was at a pretty fast constant speed, D beat the speed of A, eventually becoming the fastest car. However, based on which one went the farthest, A still wound up, if this was a race, A would still win. Even though D was fastest by the end of 20 seconds, it still didn't go as far as A did. I know that because D is the area under the curve of a V versus T graph, and A has the most area beneath it for the entire time. And then they said specifically, oh, that says from 0 to 10, not 10 to 15. Let me fix that. So from 0 to 10 seconds, it doesn't matter. A still winds up having the most distance because it has the most area under the curve. So its high speed from the get-go did actually send it the farthest. And if this was a race over the fixed distance, A would have won. So anyway, 12 is A because it has the most area under the curve. 11 and 12. All right, let's move on. So for 13, we have an object rolling down a ramp. It starts from rest. It rolls 10 meters down that ramp, and it takes 2 seconds to do so. And it's going to speed up as it rolls down the ramp. And what the problem wants to know is, what is that acceleration? All right, we don't know the speed at the end of the ramp. That's okay. We don't need it. Based on the stuff that we're told and the stuff that we need, page 6 of the reference table shows me d is VIT plus 1/2 AT squared. I have everything I need. Plug in and solve. Substitute with units. 0 times anything is 0. 2 squared is 4, and then half that is 2. Get A by itself. A is 10 over 2, or 5. And we know the units for acceleration are meters per second squared, so that would be choice 2. Careful, this doesn't happen that often on the regions, but it does happen sometimes. Don't pick choice 1 because the units are wrong. We know our acceleration units are meters per second squared, not meters per second, so it's choice 2, not choice 1. Next. Okay, so in 14, we have a car, and it's accelerating from rest at 3.2 meters per second squared. Find the speed after it's traveled 40 meters. All right, so gone 40 meters, starts from rest. We want to know V final. We don't have the time. We don't need the time. We got Vf squared is Vi squared plus 2AD right from page 6 of the reference tables. Let's go. Substitute with units. We get Vf squared is 256. Now be careful, the V final is not 256 meters per second. That's crazy fast. I need to get Vf by itself, so I square root both sides. End up with a V final of 16 meters per second because it's a speed. It's not multiple choice, we just box our answer and we go to the next page. 15 through 19 are all based on one graph. So we identify the type of graph it is. It is a V versus T graph. Reminder before we look at anything, the slope of V versus T, of course, we know is acceleration, and the area under the curve of a V versus T graph is distance or displacement. And actually, this is a speed graph. So since it's speed is a scalar, distance is also a scalar. So we're going to put distance for area. And so 15, when's the acceleration from 3 to 5 seconds? That would be the slope from 3 to 5 seconds. You could also do delta v over t and get the same answer. I wind up with 7.5, and we know the units are, of course, meters per second squared. If you take the other approach, you get the same answer. Now, 16, I was talking to a couple of different people about number 16, and some people were like, oh, I think I'm overthinking it. And yeah, don't overthinking it. Don't overthink it. If you need speed from a speed graph, read the graph. Question says, what's the average speed from 6 to 8 seconds? So there's two ways you can do this. You could do v equals d over t, and then take the area under the curve. There's that triangle bounded by EF up top from 10 to 25 meters per second, and then a square beneath it. Find those areas and then divide that by the time, and that will give you the average speed. But you don't actually have to do that. You can take the start speed and the end speed and average them. So at 6 seconds, we can see at 6 seconds the speed is 25 meters per second, and at 8 seconds the speed is 10 meters per second. And it says it wants the average speed, so average those numbers. And so 35 divided by 2 is 17.5, and since we're talking speed, that's meters per second. And that's your average speed. I wrote in the longer but just as valid way of doing it, using the d as the area, doing v equals d over t. Area is 35 meters over 2 seconds is 17.5 meters per second. So no matter how you come at it, you wind up with the same answer, 17. Speaking of finding distance by taking area under the curve, we have number 17. Find the distance traveled in the first 3 seconds. Okay, let me first show you a common wrong way of doing it. A good thought, like in terms of physics thinking, it's a good thought, but it doesn't work out. So let me tell you what I'm talking about. First of all, people start with v equals d over t. In solving for d, we get d is v times t, which is true. All right, but here's where we go south. Here's where things go wrong. So right, in the first 3 seconds, and you look at a speed, and you're like, all right, so speed is 10 meters per second, and the time is 3 seconds. And you wind up with 30 meters. Except the answer is not 30 meters. The answer is 25 meters. So it's like, wait, what went wrong? So 30 meters is not right. The reason why is because this 10 meters per second right here, it's not 10 meters per second the entire time. It's 10 meters per second from 1 to 3 seconds, or from B to C, but from A to B, or 0 to 1 second, it starts at 0 meters per second and winds up at 10. So it's accelerating in the first second, then it's constant speed from B to C. Now, you could find the average speed in the first second, do that section, and then use the 10 meters per second for B to C, and then do that section and add them. But in so doing, what you're going to be doing is taking the area anyway. So when we take the area, we are in fact doing v equals d over t, but we're accounting for when the speed is constant and when it's not constant. So that's kind of like the explanation there as to why we take the area, but we're going to take the area. But again, to be clear, those people that are doing v equals d over t or d equals v times t, that's not crazy. That is a good thought. It's not like you're like coming up with some weirdo thing that has no basis in physics. But we have to accommodate for when the velocity is changing. All right, anyway, taking area. I like to break into sections. We have that first triangle for AB, and then we have the square for BC. And so for the first section, AB, when we're accelerating, we get 5, and for BC, when we are not accelerating, or at constant speed, we get 20, and of course the units are going to be meters, so when we throw that all together, we get 25 meters for the total distance. That's 17. And so 18 asks, where's the greatest acceleration? Of course, we know from a v versus t graph that the acceleration is the slope. If the acceleration is the slope, we look for the section that has the greatest slope. And in terms of like basically the greatest slope meaning the steepest slope. And you can see that 3 to 5 seconds, that section has a pretty good slope there. That rise over run, that would be 15 over 2, that's 7.5. But looking at AB is a little bit steeper with a rise over run of 10 over 1. I worked out all the slopes, but we can see that AB is the steepest at 10 meters per second squared. So that would be AB for 18. All right, 19, the last question dealing with this particular graph. It says from 8 to 10 seconds, what's the speed doing? So we just read the graph. I mean, it's a speed graph, so read the graph. So we can see that the speed is decreasing from 10 meters per second to 0 meters per second over 2 seconds. So that's choice 3, decreasing. Okay, getting close to the end. Now, 22. Which pair of graphs represents the same motion? So the way you do these guys is by remembering, because we have a d versus t graph and we have a v versus t graph, right? Remembering that the slope of the d versus t graph is velocity. So we look to the v versus t graph to figure out what the slope of the d versus t graph is doing. Well, the answer is choice 3, but let me explain why it's choice 3. All right, so the v versus t graph on choice 3 has a steadily increasing value over time. So that v versus t graph is positive, that it's in the first quadrant, so the velocity values are positive, and those values are increasing from 0, getting a higher value, going up the y-axis, getting bigger value. It's speeding up. So I would say that velocity is positive and increasing, which means that the slope of the d versus t is positive and increasing. So positive slope and getting steeper. When I say an increasing slope, it means getting steeper. So for instance, if I drew this, that's a positive slope, but that's a constant slope. That rise over run is constant over its length, so that is not right. Instead, I'm going to draw a curve where it starts off positive and shallow, and then as it goes, it gets positive and steeper, and then positive and steeper still. So if I go along its length, you can see what I am getting at. And there's my curve. I have a positive slope, but shallow in the beginning. I have a positive slope and steeper at the end, with a positive slope in the middle where it's a gradually increasing slope. So those guys go together. That is choice 3. So 23, speaking of slope, we have a v versus t graph, and it says what in this graph is constant? Well, let's go over the things that could be constant. So for instance, is the displacement constant? In other words, is it not moving? Well, it's definitely moving as it has speed values. So the displacement's not constant. What about the velocity? What is that constant? No, because it's speeding up. The values are increasing. So that really kind of only leaves us with acceleration. So yeah, it's the acceleration that's going to be constant here, because the acceleration of a v versus t graph, the slope of a v versus t graph is acceleration, and this slope is constant. So 23 is choice 3. So the last 3 here, we have 24 to 26. These are all v versus t graphs. We know that. Slope of the graphs is the area, is the acceleration. What am I talking about? The slope of the v versus t graph is the acceleration, and the area under a v versus t graph is the distance or displacement. All right, 24, retarding force. You really just have to know what retarding means. Once you figure that out, you could probably answer the question. Retarding means slowing. So in other words, which one was slowing down? So if we look at all the different values, I can see that A and D are speeding up. So going through all the graphs, I can see that A and D are speeding up. A speeding up more than D is. B is a constant speed, but C is the one that is slowing down or having a slowing force. So that would be C. Next question, 25. 25 wants to know which one was not accelerating. That would be where the speed is constant. That would be B. And the last one, 6, which one traveled the greatest distance over the 3 seconds? That would be the greatest area under the curve. So the greatest distance would be the greatest area under the curve. Also the one that has the fastest average speed, that would be C. It doesn't actually say to do this, but you could actually find the areas of that skinny triangle up above and then this rectangle down here beneath this skinny triangle, and you can actually figure out how far the what is it, a car? What's happening here? Objects. So how far the object went in 26. So yeah, altogether, car C went 75 meters. Car B went 60 meters. Car A went 45 meters when I have base times height. And then D, I'm not going to do that in my head, but I can see that it has a lower average speed than C has, so D was definitely less than 75 meters. So, which object traveled the greatest distance? That would be C. And that's it. It was 6, 8 to 19, 22 to 26. And we only have about 5 minutes left in the solution video anyway, so we are done. Thank you. Bye.